but here is some notes on least squares, and I'm going to talk about it some, but I'll probably screw some of it up. So you might want to go look at those notes. Okay.
Yes.
And then just briefly, the comments about topic 5DQ2. And this is probably the first comment is something that probably should have been said earlier in the course. Because one of the things that's new to you guys is just writing down proofs, right? And
Yes.
so let's look at these kind of separately. The second one is sort of specifically about least squares. Okay. So the first comment here is basically so the thing you're trying to prove is this if and only if. So, the thing you're actually trying to prove is a complicated thing because you're assuming this x hat thing is a least square solution. So that's fixed, right? So in this discussion, this x hat here is a fixed least square solution, right?
Yes.
So that's something you know. Okay, now I'm going to say in a minute what that means. So we're not worried about that at the moment. But then what you're trying to prove is this thing here, that y equals x hat plus z for some z, which is in the null space of A, if and only if y is a least square solution to ax equals b, right? So there's an if and only if here that you're trying to prove, okay? Right, and when you're trying to prove an if and only if, there's two directions. You're saying if this side, then that side, right? And then you're turning it around saying if this side, then that side, right? So there's kind of two things you're trying to prove in an if and only if, right?
Yes.
So this is the logic part. This isn't kind of the real linear algebra part. This is just the logic. So when you're proving if this side, then that side, right? Well, that means you assume this side is true. You take y such that y equals x hat plus z for some z in the null space of A, right? So you fix that thing. And then you prove this, that y is a least square solution, right? And then when you turn it around and go the other way, you assume this, y is a least square solution, and then you want to prove this, right? So that, the logic here is like that, right? So the logic is in whatever you're going to write up, if it's an if and only if proof, you're going to have two pieces. One of it's going to be proving the kind of left to right direction, going from here over to there, right? And the other part's going to be proving the kind of right to left direction. Assume this and prove that, right? So that's just sort of the basic structure without any real linear algebra content, right? But that's what you have to do. Okay.
Yes.
Kind of makes sense. So when we talk about that's what we want to do. Okay. Now we're gonna get there, but I do want to say something about I want to expand. So I'm going to give you the definition of this, but then I want to expand on where it's coming from, right? And at some point, I'm going to do a little bit of hand waving and then say, go read this thing up here where I parse it out more. Okay. Or the book. I mean, your book is actually very good, right? So what the book does and what I do shouldn't be too different. I mean, and once you kind of understand things, you would see that we're doing basically the same thing. Okay. Okay. So this is the main thing here, right? So the main thing here, whatever you did, if I gave you a 0 on it, it probably means you're using the wrong definition. What does it mean to be a least square solution of ax equals b? It does not mean, y is a least square solution, does not mean ay equals b. If ay equals b, then y would be a solution, right? Not a least square solution. It would be a solution, right? Generally, when you have a least square solution, there is no solution. Right? It doesn't exist. That's the whole point of having a least square solution, right? I mean, there's a lot of different visualizations, right? But generally, when you're doing like a least squares things, you've got some data, little data points. Sorry, I'm trying to make those like dots, right? And then you try to fix the best line that goes through those dots, right?
Yes.
And an actual solution would be a line that went exactly through those dots, but there's not one, right? It doesn't exist, right? So typically there just is not an actual solution, right? So I think everyone who turned it in thought that they were trying to come up with a y such that ay equals b, but that doesn't happen, right? It's not true that ax hat equals b. That's just not true, right? X hat is a least square solution. It's not true that ax hat equals b. That's just false, right? So the definition, let's say, I mean, this is not really, I'm going to explain this. I'm going to try to say that, okay, we want to sort of give why this thing is the definition, but let's just say that, according to the book or according to whatever, that this is the definition of being a least square solution, right? So y is a least square solution to ax equals b. What does that mean, right? That means this. It means this thing over here, right? That a transpose a y equals a transpose b, right? That's what it means. It does not mean ay equals b, right? It means this, right? And this is called the normal equation, right, for least squares. Okay, so that's important, right? You need to know what you're actually trying to prove, right? You need to know what you're assuming and what you're trying to prove, right? So I'll tell you what, let me turn it around. I talked to one of your other classmates and I sort of expanded on why this is what we want. I'm going to do it a little bit differently this time. I'm going to just take the thing we're trying to prove. I'm going to use this definition, and actually I'm going to try to get you to do it, right? I'm going to try to get you to use this definition to prove the thing we're trying to prove first, okay? And then we can come back and look at why this is what we want to be looking at. That's where the real theory is. Like, you should really understand why this is what you're looking at here, right? I mean, right now I'm just saying this statement over here means this thing over here, right? But there's a deeper question, and that is why, right? Why does this thing over here mean that, right? Because that's not at all clear at the moment. Okay, so but let's not worry about that at the moment. Let's just do this proof first. Okay, using this definition, and then we'll come back and look at why this is what we want. Okay.
Yes.
So let's do it in that order. Okay, so this has two directions. So like I said, we're going to prove two things. We're going to assume this side. Now, by the way, we're assuming this. So let's just get down what we're assuming. So let me clear this little scribble I made. Right. So we're assuming x hat is a least squares solution, right? So let's make sure we understand that. We're assuming x hat is a least squares solution. So what does that mean? That means A transpose A x hat equals A transpose B. This is our assumption. Sorry, you've met with me enough to know my handwriting sucks. Assumption on x hat. All right, that's our standing assumption on x hat, right?
Yes.
That's what it means to say x hat is a least squares solution, right? It does not mean ax hat equals b, right? It means this thing there, right? Okay,
Yeah.
now what we're going to do is we're going to assume this side. Okay, we're going to assume y is equal to x hat plus z for some z in null space of A, and we're going to try to prove y is a least squares solution to ax equals b. Okay, so let's get that down. So we're assuming y equals x hat plus z for z in the null space of A, right? So that's what we're assuming. And we're trying to prove here that y, well, yeah, okay, I'm going to write it out first. Then we're going to sort of restate it. So y is a least squares solution to ax equals b. Okay, so that's what we're trying to prove. This direction, right? We're assuming this and proving that. Okay.
Yes.
Right. Okay. So we don't really need to expand on this. We know what that means because it's just there's no definitions to unpack here except for this bit, right? We know what x hat is. Okay. But let's say, what does this mean? So you tell me, based on what I've just said, how do we sort of unpack that? What do I really want to write there, right? What am I trying to prove?
I guess that would mean that y is a least square solution. So A transpose AY is equals to A transpose B.
Good. Okay, good. So that's what we're trying to prove here. A transpose AY equals A transpose B. That's what we're trying to prove, right? That's what we want to prove. Okay, good. Okay, so we're going to take this y right here, and we want to prove that, right? So now there's kind of an obvious thing to do. You just compute A transpose A y. Just compute it, right? Y is that thing right there, right? So that is A transpose A, and then x hat plus z, right?
Yes.
Okay. Now this is just a matrix, right? And I'm multiplying by this sum. So how can I expand this?
A transpose AX plus A transpose AZ.
Good. Okay. And what can you tell me about A transpose AX?
That's equals to A transpose B.
That's equal to A transpose B, which is what we want on the right-hand side, right? What can you tell me about A transpose AZ?
I guess that would mean it's 0.
So this is 0. Now you do need to say something. Why do we know this is 0? We know that Z is in the null space of A. So we need to say something since Z is in, but it's not the null space of A. We're multiplying by A transpose A here, right?
Yeah.
But Z is in the null space of A. So what do we know here? Do I know that A transpose A Z is also 0?
A transpose AZ, yes.
We know it's 0. And I mean, in this case, we can actually see it because we know that AZ is 0, right?
Yes.
Because of that, right? So
Because
we know that. So we know
is it
that
because
A
of the null
transpose.
space?
I'm sorry. Say that again.
You said AZ is 0. Is it because of the
Because
null
of this.
space?
Yeah, that's what it means, right?
Yes.
Yeah, we're assuming that Z is in the null space of A. That means exactly that AZ is 0, right? That's what it means, right?
Yes.
So if AZ is 0, then A transpose times 0 is also 0, right?
Yes.
But in particular, I can say because Z is in the null space of A transpose A. Right. I mean, in some sense, here's a thing you've done earlier. I mean, this is a good thing to keep in mind because it's important. It's really important to what we're doing now. The null space of A transpose A, sorry about that, is exactly equal to the null space of A. And you've done a previous exercise where you've shown that.
Yes.
Right. Okay. So and this is always true, and this will be important for us, right? And so we know, for example, if the columns of A are linearly independent, right, then this thing is invertible, right? That's actually very important for this whole discussion, okay? Right, because this would be like an M by N. So you think of this as being M by N, right? And generally you think of M as being like a lot bigger than N, right? So these are like tall vectors, but there's not very many of them, right? And so this is N by N, right? So you think of this as kind of being a small square matrix, and this is being kind of a tall, thin matrix, right? So, and this is usually a data matrix. So you have a lot of data points, but not very many variables, right? These would be like each column would correspond to a variable, but each row would correspond to a data point. So you usually have lots and lots and lots of data, but not that many variables, right?
Yes.
And so when you're in that kind of situation, typically these because this is sort of random data, right? So typically these columns are going to be independent of each other. They're not going to have any dependence, right? And so this matrix here will be invertible, right? Okay, but in terms of this proof, we're done, right? Because this is A transpose B, right?
Yes.
Okay. So that's what you want, right? So now we've proved this side, and that means that y is the least square solution to ax equals b, right? Which is what we wanted to prove, right? In that direction, right? So good. All right, good. So you got it?
Yes.
Okay, so now let's sort of flip it around and go the other way. We're going to say, suppose y is the least square solution to ax equals b, and we want to see that y is equal to x hat plus z for some z and null space of A. Actually, I think I can just keep on with the same thing, right? So here, let's just sort of, whoops, didn't mean to quite cut that off, but there we go. Okay, so here we're going to assume this side over here, right? And I may as well just write what we're going to assume. We're really assuming this, A transpose A, y equals A transpose B. That's what we're assuming, right? And we want to prove that y equals, in fact, let's rewrite this a little bit, right? So sorry, let me erase that little bit of stuff there. Okay, go back to this. We want to prove this, but what's another way of saying this? I could rearrange this, right, and say that, so what is z? Z is y minus x hat, right?
Yes.
So I could rewrite this as saying I want to show that y minus x hat is in the null space of A, right? So I can just write it like that. I want to show that y minus x hat, because that's what z would have to be, right? Is in the null space of A, right?
Yes.
Okay, so let's see if that's true. So what I have is I have this here, right? But I also have this. This is a standing assumption through the whole problem, right? Is that I have this, right?
Yes.
So I can subtract, right? I can subtract this side, right? So I get A transpose A y minus A transpose A X equals, and this is just A transpose B minus A transpose B, so that's 0, right? And now what can I do with these? I can
move it over to the other. You can move it one to the other side and make them equal.
I don't want to do that, right? I'm trying to show that this is in the null space.
Oh, okay.
Right? But I can just, this is just a matrix times a vector. I can just factor out the matrix, right?
Yes.
So A transpose A times Y minus X hat equals 0, right? But that, what does that tell me? It tells me that at Y, so this tells me what? It tells me Y minus X hat is in the null space of A transpose A. And now you really do have to use this thing you know from before, right? You know that that's equal to the null space of A, right? You knew that from ahead of time, right?
Yes.
And so, and that's what you wanted, right? So we've got exactly what we wanted here, right? Okay, does that make sense? All that makes sense, I think, right?
Yes.
Okay. So now the more important question, I think, in the long run is, why is this the thing we're looking for, right? I mean, that's kind of the more relevant thing. Like, I wouldn't spend a lecture on this, right? I would sort of say this is a homework problem, sort of explaining why this is what we're looking for in the first place. Well, that's kind of a lecture, all right?
Yes.
So let's look at it a little bit, and then I'll sort of tell you what you get, and I don't know, we can try to figure it out, but I think without sort of preparing for it, maybe I would mess it up, but we can see. Okay, so here, like, here's the main theorem, okay? And in fact, this theorem is probably more advanced than what we would. Tell you what, I'm going to say it the way I would think it, and then we can then maybe we can just sort of prove the case that we're interested in. So that, you know, I mean, in general, you don't actually just think about these things in terms of finite dimensional vector spaces. You actually think much more generally in terms of function spaces and all sorts of infinite dimensional vector spaces. So it turns out there's this very important theorem that says, like, if I have a vector space V, and I have a subspace S, so some subspace, and I've got B an element of V. Oh, and I got to be a little bit careful. I've got an inner product space, right? So V is an inner product space. And it can be a complex inner product space or a real inner product space, right? And again, you might want to look at my notes to see the difference in those. Usually when I think about inner products, I just think about the complex inner product because that's the more general one. And then if it happens to be real, then the results are all the same. You just have to remember that there's nothing, like when you take the conjugate of a real number, you just get that same real number back, right? So you're sort of in this situation, and sorry, I know I'm sort of stating a theorem and kind of illustrating things at the same time. So one way of drawing this would be to say, okay, my V looks like that, right? This could be an infinite dimensional space. I mean, it doesn't really look like a square or anything, right? I'm just wanting, you just sort of want to think of vector spaces as being kind of flat. They're kind of the flat spaces, right? So if you were in 3 space, right, the subspaces of R3 would be planes going through the origin, right? Yeah. I'm sorry, there's actually a few subspaces. The 0 vector would be a subspace. Lines through the origin would be subspaces. Planes through the origin would be subspaces, and then the entire space itself would be a subspace, right? So there's actually a collection of subspaces, but they're all kind of flat. I mean, you think of lines as being flat, not curves, right? And you think of planes as being flat surfaces, not curvy surfaces, right? So that's kind of the idea, right? Okay, so in this sort of weird picture way of viewing subspaces and spaces, I'm going to say 0 is kind of in the middle. And I'm going to view my subspace as kind of being like this thing here. So there'll be my S, right, sitting there. Okay. And in fact, I guess if you wanted to be a little bit, you could also say that I can always decompose V into an S and an S perp, the things perpendicular to S, right? So because I'm in an inner product space, right? So S perp will always just be the set of all V and V such that V is perpendicular to everything in S, right? So something like that. Okay, you have to be a little bit careful here. So like, if you're thinking about your room, right? Someone asked a question like this. You're thinking about like the floor and wall of a room, right? Those things aren't perpendicular, so to speak, in this sense, right? Because I can find vectors in the floor and the wall which are not perpendicular to each other, right? So in R3, you don't have two planes that are literally perpendicular in this sense, right? The best you can do is like a plane and a normal line, right? So like, you know, if you have a plane through the origin, then you take the line through the origin, which is normal, perpendicular to the plane, right?
Yes.
And that would, so if S was the plane, then S perp would be the normal line, not a plane through the origin, but a line through the origin, right? And then any vector in R3 could be written as a combination of things in the plane together with something on that line, right? So you have to be a little bit careful because your intuitions can lead you astray. Like you don't want to think of two planes in R3 as being perpendicular because they're not perpendicular in this sense, right?
Yes.
Okay. But anyway, you get a picture like this when you're in the inner product space. So in R3, this would be a weird picture of R3, but this might be a plane and this would be its perpendicular line, its normal line, right? But this is sort of a generalized picture, right? And I have this arbitrary B sitting out here, right? And I'm going to sort of think of this vector as like being a little arrow coming out there, right? Okay. And the thing is we can project into these two spaces, right? And so we can kind of take that B and get these two pieces right there, right? A part that projects into S and a part that projects into S perp, right? So we might write something like the projection, say the perpendicular projection onto S of B, something like that, right? So that may be a projection where I'm taking this and projecting it onto the subspace, right? And so we're going to call this B hat, okay? And then the projection onto the other part, right? The projection, the perpendicular projection onto the perpendicular part here would just actually be B minus B hat. It would just be the leftover part. Sometimes we call that a residue, okay? Okay, but the theorem is that this B hat is unique, okay? There's only one B hat like this, okay?
Yes.
So now the way the theorem goes to prove it is a little bit tricky. So what you actually do is you look at this quantity here. You look at the set of all, look at the norms of sorry, I've got this S here. So look at the norms of everything in S minus B, okay? And take the minimum of all those things for S and S, okay? So this is a norm, right? So in, you know, in the normal vectors, this is just the length of the vector S minus B, right?
Yes.
Okay. You know, in more general spaces, like in function spaces, this may be the, you know, the sort of inner product of S minus B and S minus B. So it'd be like the integral of S minus B squared, right? Or something like that. So you've seen a few strange inner products at this point, but the point is this thing here is always a number greater than or equal to 0, right?
Yeah.
Okay. If it were equal to 0, then that would mean that there are points in S that come right up, right, in the limit touch B, right? And then the theorem that we're going to have here would see that B is actually in S in that case. Okay. So the main thrust of the theorem is that there is actually a B hat that realizes this. There is actually a single B hat such that B hat minus B equals this min, and B hat is in my space S. Okay. So that is the kind of abstract theorem that's underlying least squares, okay? So basically, if I give you a subspace, I give you something that's not in the subspace, right? There is a unique projection of that thing, of this thing out here onto that subspace, right? That B hat, okay? So in other words, this function right here is well defined, okay? And it's actually linear, right? If I take projection, the perpendicular projection of, you know, B1 plus B2, then that's going to be the projection of B1 plus the projection of B2. If I take the projection of alpha times B, it's going to be alpha times the projection of B. Okay, so this is actually a linear function too that projects, okay? Which is a hint, that means it's given by a matrix, okay?
Yes.
Okay, so so that's and so now here's the part that I'm gonna fudge on a little bit. So the way we do it in sort of beginning linear algebra, like in your class, right, is instead of proving this very general theorem of this sort. So this actually uses analysis in some sense because we're looking at a min, we're sort of considering limits, and we try to build this b hat. You know, so there's a lot of sort of math that goes on here, right? What we do instead in finite dimensional vector spaces is we just try to directly compute the projection matrix, right? We just try to directly compute it. That's what we aim to do. Okay. Okay, so in our case, we don't have an arbitrary S here, right? So in our case, we have this, we're in this case here, we're sort of looking at the set of all AX, right? So A, you know, A is M by N, right? So its inputs are in Rn, right? So we want X and Rn, right? So this is the same thing we might call the range of A, right? And that's the same thing as the column space of A, right? So these are just words for the same thing, right? So in our picture, we had sort of, our picture here is Rn, right? And our little bit here, right, is the range of A. So I guess the book just abbreviates it RA, right? So the range of A is right there, right? Right, and our B, we think of our B as sort of sitting out here, right? B, right? And we're trying to find the point in the range of A as close as we can to B. So what does that mean? We're trying to find the X such that AX minus B, right, is minimal, right? So in other words, we're sort of looking in the long run, we're looking at the all of these things, AX minus B, for X and Rn, all right, and we're finding the min of those things, right? And then we're trying to say, well, that is actually equal to some AX hat minus B, right? We can actually find a specific thing here. You know, that's our B hat, right? So this is actually coming from this theorem, right? This is a subspace, the set of all AX, right? When I look at the images of things under A, right? That's a subspace, right? So I know from this theorem up here that I have a unique B hat in my subspace, right? So what does it mean in this case for B hat to be in the subspace? It means there's some X hat, right? Such that AX hat equals B hat, right?
Yes. So
Okay.
what I'm getting is right now you're looking for from the projection B, from projection S, which is B hat, right?
We're looking at the projection of B onto the subspace S, the orthogonal projection, yes.
Okay.
And that thing is B hat, right? That's what we're calling B hat. And I haven't proved it. I've just claimed that thing exists, right? That's all I've done so far. Okay, but part of the theorem, but also part of the theorem, right? And now in our special case, right, where we're doing least squares, is we do have this matrix A, and the special S we're looking at happens to be the range of A, right? It happens to be this set right here, right?
Where?
Well, this set right here, right?
Okay.
It's the range of A. So the S we're interested in here is really just the range of A, right?
Yes.
Okay, and so part of my theorem here is that the B hat that I'm looking for is in S, right? So in particular, in my case, I have that B hat is in the range of A, right? But that means that B hat equals A X hat for some X hat, right?
Yes.
Okay, but here's where you want to be careful. The B hat, this projection, that part right there, is unique. That's part of this theorem. There's a unique B hat, right? Which is as close as possible to S. That is unique, okay? But like we just proved, this is not. There's lots and lots of X's that might map to this B hat in this way, right? I mean, that's not quite, yeah, I guess that's what I want to say, yeah. I mean, because we're not looking at B, right? I guess the thing is, before I was saying that being a least squares solution is not saying that AX hat equals B, right? But it is saying that AX hat equals B hat, right? That's the difference. You see, there's a difference there, right? So we're not saying we're finding a least squares solution. We're not finding this actual solution to AX equals B, right? What we are finding is a solution to AX equals B hat, where B hat is the closest thing of the form AX that happens, the closest thing to B that happens to be of the form AX, right?
Okay, I see what you're talking about now. So you're
Okay,
saying
and
it's not exactly that line B,
it's
but
not
rather it's
B.
the
B
one
is out, yeah,
closest to.
yeah, B is
Okay.
out here, right? It doesn't exist in the range of A, right?
Yes.
So it doesn't exist, but there's that B hat right there, and that B hat is unique, right? And it is in the range of A, right?
Yes,
So
I see.
what we're looking for is the X. So when we say X hat is, whoops, a solution, a least squares solution to AX equals B, what we really mean is we mean X hat is a solution to a X equals B hat, not B, but B hat, right? That's the difference.
Yes.
Okay, and there may be lots of those, right? There may be lots of X's that give me this B hat. Now, again, you want to keep in mind that the B hat itself is unique. That part is unique, okay? See, so the theory is telling us something a little bit strange. It's telling us that the B hat is unique. It's not telling us it doesn't really tell us anything about it doesn't tell us anything interesting at all about the X hats, right? Because the B hat we know is in the range, so we know it happens to be equal to some X hat, right? That's sort
Yes.
of trivial, right? The interesting thing is that B hat exists at all, right? The thing that's closest to the row space of A exists, right?
Yes.
I mean, the thing in the row space of A, which is as close as possible to B, that thing exists. That's the thing that's actually interesting here. Okay.
Yes.
Okay, so now, right, and there's lots and lots of ways you could go on with the theory here. So one thing I could do is I could start talking about the theory of projection operations, right? So and then orthogonal projection operations and Hermitian operations, and we will do this. It's sort of, if we had 15 weeks, we would do all this sort of stuff, but we don't, so we can't quite do everything, right?
Yes.
So some of these I may give you as problems like in exams or something, right? So but here what we do instead is we give you a particular matrix that does the projection. Okay. So let's see that works. Flip, there we go. Okay, so what we do is this: we say, okay, look at this matrix here, and we make it, and for now we make an assumption. We assume that the columns of A are independent, right? Remember, that was my sort of assumption, that I had these kind of long data columns, right, without too many variables, right? So I think
Yes.
of this as a tall matrix. So that this thing, so this would be M here and N here, right? So you think of N as being small in some sense. So this would be N by N, that N transpose A would be N by N. And so it's going to be invertible. We're assuming it is invertible, right? And then A transpose B, and then A, okay. And this will give us our B hat. Okay, that's what we're going to claim. Okay, so I could call this big old matrix here P, right? Because it's a projection matrix, right? So in fact, P of B is the perpendicular projection onto the range of A, of any vector B, right? So this is actually our projection matrix right there. Okay. This whole thing is our projection matrix, that whole thing right there. Okay.
Yes.
Okay, now we can prove that this actually works. I mean, that's a computational thing, right? So so if I want to, maybe we'll do that. I mean, we'll see how tired you are in a minute, but let me sort of derive our normal equations first, right? So suppose we know this, right? Suppose we know that this thing is giving us the correct B hat, right? So again, notice that our focus isn't on the X hat, it's on the B hat. Suppose we know that we're getting that thing correct, right?
Yes.
Okay. And let me just point out too, if it happened to be the case that that A was actually invertible, right? Then notice that this whole thing that we have here, A transpose A inverse A B would become A, and then we put then when we do the inverse, it sort of flips these things around, A inverse A transpose inverse, right? When we do an inverse, it changes the order, right? Oh, sorry, this should be A transpose. Yeah, A transpose. I had it right over here, but not over here. Right? And then so these just cancel out and those just cancel out, right? So this is just I times B, right? Which is just B, right?
Yes.
So this is saying if B happens to already be here, right? Then you just get B back, right? Or if you, if you like, if your matrix happens to be invertible, then you get solutions for everything. So I mean, if your matrix is invertible, then this thing is already all of Rn, right? And so when we project, then we just let's see, is Rn right? Sorry, Rm, right? The range is actually in Rm. So when we project, right, we just get back in. Let me think for a second. Sorry, am I saying that right? The range Ax, yeah, that's right. Rm is right, right? So we just get B back, okay? Because we're just projecting into the entire space, so we don't have to. We're not projecting onto anything, right? We're there, right? Does that kind of make sense? I mean, maybe it makes more.
What I'm getting that you're saying is that if you're projecting B onto RA, you're saying you're projecting it on Rn because it covers the entire space.
Yeah.
Okay.
So there's no project, right? If I was in a situation like this where my vector space was here and I have this little subspace here, and I'm projecting a vector outside of S onto it, then I would project it onto some little vector there, right?
Right. Yes.
Okay, but if I happen to have a vector that was already in S, right, and I tried to project it into S, it just wouldn't move. It's like, it says I'm in S already. What are you trying to do, right? So it doesn't do anything, right? So that's kind of the idea here. Okay. Okay, but let's sort of parse it. So suppose we knew that this matrix did what we wanted it to do, right? Then let's see how we derive our normal equations, right? So we have this, right? And so what this says is it says A. So I'm gonna forget the entire thing here. I'm just gonna look at the part here. I'm gonna sort of focus on this part. Remember, and I said what we were actually trying to do in the least squares case is we were actually trying to find a solution to Ax equals B hat, right? We're trying to get to the place closest that we can, right?
Yes.
Okay, but this just gives us that, right? This says, okay, fine, I will just compute this guy here. I'm just gonna call this X hat, right?
Yes.
Okay, and when I call this thing X hat, well, what do I get? I get that A X hat equals B hat, because that's just exactly what this says, right?
Yes.
Okay. Right, and now we can just sort of rearrange this, right? We just rearrange it to say, because this is invertible, I can just multiply both sides by A transpose A, right? And so, oh, sorry, and this is transpose here, not, I gotta keep getting that right. Yeah, that one's a transpose, this one's A, right? So that's A, okay. Right, so when I multiply both sides by A transpose A, then what I get is I get A transpose B equals A transpose A X hat. Right, so notice that is our normal equation, right?
Yes.
Okay. Okay, so and more to the point, if I take anything, and if I take any Y such that satisfies this, if I take any Y such that A transpose B equals A transpose A Y, right? Take any Y that happens to satisfy that, right? And then I apply A of Y, right? So I look at A of Y, right? Well, then what I can do is I can say, I can take this, I can sort of move it over and say, well, this means that Y equals A transpose A inverse A transpose B, right? And so when I do A of Y, I'm going to still get B hat, right? Because I'm seeing this thing up here.
Yes.
Right. Okay, I'm going to let you think there's a little bit of fishiness going on right here because I seem to be getting this unique Y. So I will say that later on, we're going to have a notion of something called pseudo inverse. This will be at the very end of the class. So in the end, and in fact, when you do an inverse in MATLAB, it doesn't actually take an inverse. It takes something called the pseudo inverse, right? And so it turns out that the things we can find here would actually come from pseudo inverses, not necessarily inverses, right? And so this Y wouldn't be uniquely described this way. Anyway, there's sort of a lot of stuff you'd have to say to get that exactly right.
Yes.
But the upshot of all this is, if you believe this thing up here, right? If you believe that this projection matrix here, this long complicated thing, gives me the right B hat, right? Then you have to believe that when I'm looking for a least squares solution, I just need to find something satisfying this, and that's the normal equation, right? That I gave you. All right. Because I said Y is a least squares solution if and only if A transpose A, Y equals A transpose B, right?
Yes.
So this is the normal, this is what we call the normal equations, right? Okay.
Okay.
So that's where that comes from. It doesn't, this isn't really in some sense the major in definition. The major definition is this projection matrix right here. And then proving that that's the right projection matrix, right? Now we could try to do that. I mean, that probably isn't so hard. Do you have the stamina, or do you want to quit and think about it?
You just gave me a lot of information, and
Yeah,
I'm not
yeah,
gonna lie,
yeah.
it did get me confused at one point, but I did get it later on.
Okay.
So, I don't even know how much time I have. I feel like my aunt's calling me.
Okay, yeah, that's fine. Yeah. So think about this. And if you want to see more, I mean, it's written in the notes, right? So
Yes.
like I derived this matrix and how it does what it's supposed to do in those notes. So you can just look at those.
Yes. I just didn't, because I read the notes, but like that one part in topic 5. I don't know. I feel like I just skipped it by mistake. So I never saw that one
Yeah.
space
Yeah.
out of
There's,
both topic 5 quiz.
yeah. There's a lot of stuff that I posted for these last few topics because they're important topics and they're rich. There's a lot of stuff there. So
Yeah,
so do take a look at some of that stuff.
Yeah, I'm just gonna read through the PDFs. Then I still have the videos for this week open, so maybe I'll just go through them again.
Okay. Yeah. I'm sure that Strang talks a lot about this projection matrix too. So I'm almost positive he does it in exactly the same way.
Yeah, I just learned better with like examples and someone telling me examples rather than them just writing everything out. So this really helped.
Yeah, good. You know, I would say one thing, like here's an interesting thing for you to think about. You know how to find the projection of one vector onto another vector, right? Like the
Yes.
orthogonal projection of how do we do this? Yeah, I guess we have a vector U we're interested in. We're interested in finding the orthogonal projection of U onto V, right? So the typical picture is like in R2, right? I would have, say, a vector that I'm interested in, U, right? And I have some other vector I'm interested in, V, right? And I would like to find the orthogonal projection down from V onto U, right? And so that would usually be this projection here, right? And our usual formula for that would be the inner product of U and V over the inner product of U. That's our usual formula for this projection. Oh, and then times U, right? So this is our usual formula for projection of a vector onto another vector. The orthogonal projection of a vector onto another vector, right? You can derive this formula right here. I mean, so if you think about this a little bit, so like our definition of V transpose U, I'm sorry, of UV, right, is really V transpose U, right? Of the inner product of U and V is V transpose U, right? And we're dividing by U transpose U, right? And so that would be the same as V transpose U inverse U. Is that what we want to say?
What about the multiplied by U?
Sorry, say it again.
Like, you know how in projection U onto V? Wait.
Yeah,
Yes?
then you multiply by U. Yeah, I'm just looking at that. Oh, right, and then times U. That's like the B. Okay, the U is like the B though, right? That's like that part, right? So
Yes.
I kind of don't want to think about that. I'm just gonna get you confused, but think about it correctly, right?
No, I see what you're trying to get at.
And you'll derive this from this formula up here. You have to think about it correctly. I'm just not at the moment. So I don't want to confuse any further, but you can get our usual projection formula from this one, right?
Yes.
If you somehow think about it right. Okay.